targets. I mean, 2 more people to encourage to consider joining the math team. We need at least 2 more people. We'd like to have more than 2 more, so we have a backup. And what I've seen, the first meeting was Friday, and it just is a great review of calculus and some pre-calculus stuff too. It can only help. I mean, there's no downside to it. There's no pressure. Nobody gets anything negative about it. I think will be fun, and it'll also be a great opportunity to bone up, improve your math skills, and that can only help you, not only in this course, but in physics and your engineering and whatever you're going into. I think it can only be a positive. Okay, enough of that, I guess. Okay, we were doing, if my memory's right, just finishing 12.1. We had finished the section. We're doing preliminary questions. I think we ran out of time before we were able to finish the preliminary questions. Is that where y'all were? Okay. I believe we're on question 4. And let me see if I can get a slideshow started here from this current slide. Oh, and maybe we'll even turn on the projector for you today. Okay. Now, for some reason, all I'm getting is a black screen, but it does that, it seems like. I don't know why. Here we get something more. I don't know if you can see it, but it's presenter view. So let me get out of that and into this, I hope. Okay, we're getting closer. All right, good deal. First, any questions, anything we've done up till now? Please join the math team. Okay. All right. And by the way, only Y chromosomes here today. Where are the X's? I don't know. But anyway, let's move on. No questions? Then preliminary question number 4, page 633, section 12.1. What are the components of the 0 vector based at 3, 5? What are the components? Woo, let me get my pen better set up than this. Okay. Of the 0 vector based at the point P equal 3, 5. Yeah. What are the components of the 0 vector based there?
I'd say it's 0.
You're absolutely right. It's 0, 0. Wherever the 0 vector is based, it's 0, 0. Or if it's 3 dimensions, 0, 0, 0. Or 17 dimensions, 0, 0, 0. Okay, you got the idea. Just because it's based there, that would be the initial point and the final point, but it wouldn't, its components are still 0, 0, 0. Now, if that ain't right, it better be. So let's see what the back of the book says. If I can find the back of the book. 12.1, no, 12, yeah. 12.1, number 4, 0, 0. Very good. Okay, number 5. True or false? Okay, A. Vectors V and negative 2V are parallel. That sounds like it better be true. Number B. The vectors V and negative 2V, or not 2V, point in the same direction. All right, that's definitely false. That's supposed to be same direction. False. Okay, better be true, false. And in the back, it's True, false. Excellent. Number 6 isn't in the back, I don't think. I didn't see it back there. Explain the commutativity of vector addition in terms of the parallelogram law.
Take whichever base and
If you go
you can take it either way.
add these two, you form the parallelogram, or do it like that, you form the parallelogram. It's the same parallelogram, whichever one you do first. So yeah, and that answer's not in the back, but hopefully you can see and understand it. I know I gave you these homework exercises before, but just to review and repeat them. Either 1 or 3, or both if you choose. Either 5 or 7, or both if you choose. Either 9 or 11, or both if you choose. And any of the odds 13 through 17. Any of the odds 19 through 27, either 29 or 31, or both, either 33 or 35, or both, either 37 or 39, or both, and any of the odds 41 to 47. Any of the odds 47 to 53, any of the odds either 55 or 57 or both, do 59, do 61, and either 63 or 65. Good deal.
Richard said he'd be here Tuesday at 3:30.
3:30, okay. So we'll be meeting tomorrow at 3:30, probably down in my office. Now, if you're a little late and we're not in the office, because we probably won't stay there, it's too crowded and cramped, start looking at classrooms, any of the classrooms between that one and this one. If all of those are filled, we'll come up here. But if any of those are empty, we'll probably settle there. That way I can hear my telephone if it rings or that kind of stuff. And that way y'all can hear me if you come, or hear us, not me. Okay. All right. So I think we're ready for 12-2. Now, what I want to do here, I think, is discard that and pick up this. Okay. Now let's go to vectors in 3 dimensions. Okay. We've been, 12.1 was just vectors in 2 dimensions. I don't know if that was the title of it. Vectors in the plane, which is 2-dimensional plane.
I never really liked the hand thing.
The right-hand rule? I don't like it either because it sounds like right-hand rule and I'm left-handed, so never know. But anyway, the vectors in 3 dimensions, let me sort of picture it like this. I wonder what that's a foot to. It's a foot to some chair or something. Ah, I see it right there. I think I know what happened. They wax the desk to the floor, and then you move the desk, and the foot stays. That probably won't stay, but at least I got out of it. So let's just imagine the floor to wall line here. Let's call that the x-axis. This one would be the y-axis, and then this would be the z-axis. Sort of imagine that wasn't there, okay? There. And then you would have x, y, and z, and that's what they call the right-hand rule. If you point your fingers of your right hand in the direction of x, bend them to the y, then your thumb will be pointed in the positive z direction. Positive x, positive y, positive z. The right-hand rule. Now, if you flipped it over, that positive x were here and positive y were there, then positive z would be going down. Don't switch hands, okay? But that would be right-hand rule. And wherever you are, if this is positive x and there's positive y, z would be up this way, you know. So wherever you orient them, that's called your right-hand rule. That's 3 dimensions. Now, technically, vectors can have n dimensions, infinite number of dimensions. Well, I don't know. I guess it has to be finite, but it can be a large number. We're going to live in the first and second, 1 and 2 dimensions most of the time, because that's indeed where we live. People have talked about higher dimension, maybe time being one. It's just that time usually doesn't have a negative end on it, so that's not a very fair thing to say, but people do deal with things like that. Now, and I forgot this. Went into this and I wasn't paying attention. Here's Ashley. All right, good deal. Now, I'll say it again because I've said it every time someone's come in. Please consider joining the math team. We've got 6 people signed up now. It would be great to have at least 8, because that way we can have 2 competitive teams. Anything more than 8, that means if someone can't go 1, we can still fill 2 teams. So as many as you can to go, please consider doing it. It should be nothing but fun. No stress, don't lose anything. You only gain knowledge and the practice and the camaraderie and the experience. I think it'll be great. Okay. I won't be able to go to that first meet because that's the weekend that my nephew's getting married in Dallas, Texas, and so we'll be out of town that weekend. But we're going to be practicing on this campus. I'll be meeting with students Tuesday, Thursday afternoons at 3:30. Is that what he said? Anyone that wants to come and join in the practice will do. They'll have practices also Monday and Wednesday afternoon on the Birmingham campus. I don't remember what time that was set. Do you remember what Ms. Martin said her time was? There's probably going to be 2 sets of practices over there. But I believe Monday, Wednesday. I know Monday, Wednesday was when Mr. Racy could do it, and I think Monday, Wednesday was also when Ms. Martin could do it. You remember when Richard's calculus was? Okay, it's whatever the days that isn't, I think, where the Ousel wasn't. Okay. Now, I think I've explained the coordinate planes using this. Oh, and by the way, whereas the plane, when you do an x-axis and a y-axis, that breaks it into 4 quadrants. When you have space, that you have 3 coordinate axes, x, y, and z, remembering the x also goes toward the hospital out there, the y also goes down the building here, that's negative y, negative x, and negative z goes down to the first floor and below. Now you've divided space into 1, 2, 3, 4, 5, 6, 7, and 8 quadrants, octants, okay? So you're talking about not quadrants, but octants, okay? So you have octants, and we don't have names or numbers for them. This I just count as the positive one. Positive x, positive y, positive z. The one back there would be negative x, positive y, positive z. The one next door here in the fan room there, that would be positive x, negative y, positive z. Now on the first floor, the z's would all be negative, okay? But other things would be positive or negative. So you get the idea. Those are your octants. They don't have names, except usually when they're all positive, we call that the first octant. Don't have names or numbers for the others. Okay. Oh, yuck. I was saying all that, but the folks listening on, there we go. We've already done the right-hand rule. This is now describing, and this is, goodness gracious, that light is bright. Tony, you right? Okay. And I'll do it one more time. And I'll keep doing it, okay? Consider joining the math team. We've got 6 people who've already basically committed, acted like they really want to be there. We had our first meeting Friday. We really need to have 8 to field 2 teams for each. It'd be nice to have a backup or 2, okay? In case someone can't make one, more than one person couldn't make one. So please do it. We're going to have practices on both campuses. The one on this campus right now is going to be Tuesday and Thursday afternoons from 3:30 till 4:45, or we don't have to go that long as you want to go. But up to, in fact, most Tuesdays and Thursdays I'm here till 5:15. So I'll go. Technically I'm through at 4:45. Like today, I've got to leave at 4:45, but most days I stay till at least 5:15. So please consider it. We need good, skilled people like you on the team. So give us a shot. Okay. Now, this then shows a point in that first octant. How do you know this is the first octant? All they have are A, B, C's. They don't list what positive, negative, or anything else. How do you know that's the first octant? You're right. Right-hand rule. There's the x-axis going that way. Bend your fingers toward the positive y. It's this way, so that makes positive z up here. I can't twist my arm enough to do that. But if this is x, positive y, positive z, that makes these all positive. That means it's in the first octant. If you're back here, then you would be positive x, negative y, positive z. If you're back on that side, negative x, positive y, positive z. If you're down below this, that would be positive x, positive y, negative z. The one below the one back there would be positive x, negative y, negative z. The one under that one back there would be negative x, positive y, negative z. And then back there, there's a couple more. So, okay, but that's the octaves. We don't have other names for them or numbers for them. This is your octave. Now, frankly, to me, these lines don't look right. This is an isomeric drawing, and maybe they're right here, but it seems like to me they have things a little off. You've come out A units on the x-axis, and that, to me, should be the same. These 2 lines should be parallel, but they don't look parallel to me. I don't think they are, but they're pretending they are, okay? If anything, the foreshortening should be in the back, not in the front. Okay, the front should actually look bigger. But don't get hung up on that. B units out the y-axis, and these 2 lines, to me, should be parallel, and frankly, they don't look like they are either. And then C units up on the y-axis, and that sure doesn't, it may be exactly the same, but it sure doesn't. There's something off with the drawing. But you get the idea. This is the point. A, B, C. A units in the positive direction on the x-axis, B units in the positive direction on the y-axis, and C units in the positive direction on the z-axis. There. This illustrates the difficulty in drawing 3-dimensional shapes, points, or anything on a 2-dimensional board, okay? It just makes it really difficult. If you had gone negative so far on the x-axis and positive y and positive z a little bit, you'd have been in the same point on this board, but you would have been back there at that point, because every point beyond here is behind there. Like on the YZ axis here, there's another point right there, when x is 0. So it really is hard to draw 3-dimensional shapes, getting the dimension right on a 2-dimensional board. Basically, it's close to impossible, but they've done it here. Actually, in my book, on this, I don't know why, on this, that looks much better than it does there. There must be some distortion in the projection. Okay. All right. Never mind. Okay. Now, let's hit a few other issues here. Oh, I can get, I think, all of this in one slide. That's good. Okay. Here is a plane in 3 dimensions. Okay. Which plane would you name that one? Y is equal to 0, that would be the x, y plane. I mean, z is equal to 0, that's the xy plane. Okay? Because you come out x's, you go out y's, but you don't go up or down in z. So z is equal to 0 defines the xy plane. This one would be the what? Yeah, that's the xz plane where y is equal to 0. And that, of course, would be the yz plane where x is equal to 0. Exactly. Okay? Now, if z were equal to 5, that plane would just be elevated here 5. Okay? Then you'd have points x, y, 5. Every point on there would be z is equal to 5. Or drop it down 5, and that would be x, y, negative 5, or whatever. Same thing here. You can bring this out 3 units out here. That would be x, 3, z. Okay, would define every point on that plane. Or x minus 2, z. That would be 2 units back that way. Bring it out this way, 7, yz. Okay, or back that way, negative 3, yz. Okay, so you can have planes parallel to these. Those are, it would have a constant in one variable and straight line. Now, planes don't have to be like that. You could have a plane that slices down like that. That could be x, y, and z's all varying at the same time. So planes don't have to be parallel to one of these coordinate planes, I guess you would call it. Okay. Now, can anyone tell me the distance formula in a plane? Between 2 points in a plane, what's the distance between 2 points in a plane? Right here. Okay. Say one point was here and one point was over here. What's the distance? Okay. The difference in the x's here squared plus the difference in the y's here squared would give you that distance squared. So the square root of x2 minus x1 squared plus y2 minus y1 squared, that would be the distance between those 2 points. Well, guess what? In 3 dimensions, it looks almost the same. And by the way, if you haven't picked up on this yet, a line is R1, capital R1. In other words, the real number line. All real numbers are on that line. Negative infinity to positive infinity, 0, fractions, decimals, rational, irrational, all real numbers on that line. In 2 space, we call this R2, because all real numbers are represented on this line, axis, all real numbers on that one, that's R2. R squared is how they write it. Okay, we usually say R2. 3 spaces then called R3. Real numbers in every along every axis. Okay? So the distance formula in R3, or in space, 3 space, the distance between point P and point Q, wherever they are. Point P could be up here, point Q's down there in the fan room somewhere, you know. Whatever that would be, and P is A1, B1, C1, Q would be A2, B2, C2, then the distance between those 2 points, and it really doesn't matter which you put first, but since they wrote them like this, we'll write them like that too. A2 minus A1 squared plus B2 minus B1 squared plus C2 minus C1 squared would be that distance squared. So in other words, the square root of that sum of those differences squared, that would be the distance between 2 points. Now, some books, well, let's take this back. If we were talking about vectors, we'd put double bars there, meaning magnitude. Distance between 2 points, I guess is still okay, just put single bars. But some books use that for vectors as well. So get used to those two. But what do we usually think of two parallel bars being? Absolute value. Now, is there any connection here between absolute values?
Distance can be negative.
Yeah, these things are never negative because this is a principal square root. Whatever this is, positive or negative, you're squaring it, that becomes positive. This positive or negative, you're squaring it, that becomes positive. This positive or negative, you're squaring it, it becomes positive. Now, if both of these points were the same point, then of course you have 0, okay? But if it's not 0, it can never be negative, okay? 0 is not negative, but if it's not 0, it can never be negative. It's always going to be positive, and that's a principal square root, so that's positive. So in that sense, it's sort of like an absolute value. It is always a non-negative value, okay? Most of the time, positive value. The 2 points would have to be identically the same in every dimension for it to be 0. Other than that, it is positive. Okay. Now, here is the proof of that. Here's your point P, A1, B1, C1. Okay, and this plane here is the Z is equal to C1 plane. Okay, this is the base plane that's in. So this point up here is A1, B1, C is 0, okay, or C1, no, A1, B1, 0, okay. I'm sorry, yeah, that's right. A1, B1, C1. Well, that's this one. Now, what am I trying to say? If this is point A1, B1, C1, this is point A2, B2, C2. Okay. Then from this point, if you go this way, you're still at A1. That hasn't changed. But now you've gone from B1 to B2. Okay. So this would be at B2, A1, B2, C1. Then go over here, you're at A2, that's A2, B2, C1. Okay? If you did the distance of this one, that would be A2 minus A1 squared plus B2 minus B1 squared, and then this one, of course, would be 0, and that would be your distance in a plane. Square root of that would be that distance. This distance here is from A2, B2, C1 to A2, B2, C2. Well, when you do that distance, all you got is the C2 minus C1 squared minus square root of that would be that. Well, then you take that is also a right angle here, okay, because that plane is perpendicular to that one. Then this distance here, that's what you're looking for between those would be the square root of A squared, A2 minus A1 squared plus B2 minus B1 squared, plus the difference between here, which is C2 minus C1 squared, and that then, of course, gives you exactly what that is. Why didn't I blow this up? I forgot. Sorry. If I can even get it all on one slide. No, I can't. That's why I didn't blow it up, of course, okay? Sorry about that, okay? There was the first, there was the second. So this distance is indeed that formula that we had, okay? Just using a different right triangle. Okay. I believe, no, I thought this was an example. It's not yet. Okay, here what we have is a sphere. Okay, this one I can't blow up. I'll try to get that before I forget it. Boom, I blew it up. Okay. This is a sphere of radius r centered at some point ABC. Q, ABC is not on the sphere, it's the center of the sphere. And the point P has got coordinates x, y, and z. And that point P can move, that's why those are variable components. The distance between that is r. Okay? So that is a sphere of radius r centered at ABC. Now, what are they trying to show here? Okay. At any point, x, y, z, it doesn't have to be along this plane. It could be anywhere here. Any x, y, z here, they're always centered at ABC. That radius is always the same. So that radius length is always the same. So what would be that radius length? The ABC is still the C, the Q is always the same. It's just your P could be anywhere on that sphere. Okay? Of course, I've got to get out of that. I also need to get my... All right. It changed, didn't it? Okay. It was enabling me to... Well, never mind. Interesting. All right. What would be that distance R? Is what? Okay. You might say that. How do we define it? That distance. Distance formula. The square root of x minus a squared plus y minus b squared plus z minus c squared, and that's always equal to the magnitude of r. Okay, of course r is some length. Okay, what happens if we square both sides? R squared is equal, then you lose the square root, x minus a squared plus y minus b squared plus z minus c squared. Now, I'm going to do one other bizarre thing. Divide both sides by r squared. Everything on both sides by r squared. And what does the left-hand side become then? 1. So now we have x minus a squared over r squared plus y minus b squared over r squared plus z minus c squared over r squared equal 1. There is your... Remember, one of the things we did in the last chapter was look at the various shapes, the conic sections. The circle was, the typical one is x over r squared plus y over r squared plus z over r. The whole thing squared is equal to 1. This is what we got. The only difference is it's offset, the x, y, and z are offset by a, b, and c respectively, meaning your origin could be down here somewhere. Of course, it has 3 dimensions on it. And then the Q could be offset A on X, B on Y, and C on Z. That's how you represent something with an offset at its center, which is very similar to what we had before. Okay? And quite often we that's how we would represent a sphere, okay, is some sort of a form like this. Here's another way you'll sometimes see it, x minus a over r squared plus y minus b over r squared plus z minus c over r squared. You'll sometimes see it written like that. But most of the time, I think they separate the squares top and bottom. Not always, but it does. Okay, those are all equations of a sphere. But the most common might be this one, x minus a squared plus y minus b squared plus c squared is equal to r squared. That is a pretty common one too. It should remind you x squared plus y squared is equal to r squared. What do we normally call that? It's a circle of radius r, okay? And remember, then if you divide it by r squared, that's equal 1. You have that. So this would be a sphere of radius r. You just make it capital R rather than little r. Okay. I think I beat that to death. Maybe not. Here comes, what would you say this is a formula for? Circle, not a sphere, circle of, what's different about it? Radius r, that's the same. What's different? AB is the center of that circle. AB is not on the circle, but it's the center of the circle. So that circle of whatever radius r has been moved on the coordinate plane. So give me an A, give me a B. Make up one. Say it. 2, 3. Okay? Then this would be, if A were 2 and B was 3, that would be a circle of radius r. What r do you want? Give it one. 2. Okay? So here would be the center. The circle would be there, 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 there. The center is never on the circle. It's in the circle, but not on the circle. Okay? All right. So here gives this. Equations of spheres and cylinders. Now, we certainly do what spheres were. If this is a sphere of center A, B, C, 3 space, and the same radius, r, whatever that is, around that circle, this would be the equation for that. Like I said, this is the most common. But later on, we'll be dividing all 3 of those by r squared, and this will be x minus a squared over r squared plus y squared minus b, y minus b squared over r squared plus c minus c squared, r squared is equal to 1. That's also a standard equation for a sphere. Now, a right circular cylinder of radius r, now this is not the same as the radius of a sphere, but the radius of that circular cylinder, radius r, whose central axis is a vertical line through AB0. Okay? Vertical line through AB0. A is coming out with x, B is going out on the y, 0 is your C, so that's a circle of you're at point AB. Draw a circle around that in the xy plane, and then extend it up, positive z's, down, negative z's. So this is how you would express that. Now what does that look like? The equation of a circle. But if they tell you this is an R3, it's that circle, and Z is allowed to be anything it wants. So it goes up and down, that makes a cylinder. Without a top or a bottom, that extends infinitely up and infinitely down. So that same circle in the XY plane that we're used to seeing that of, that now defines a cylinder in 3 space. Does that make sense? Because in the XY plane, that is a circle. Now it's a circular cylinder. By the way, cylinders don't have to be circular. Okay? This, if that were even throughout, that's a cylinder. And certainly this is not circular. If it didn't have these things in it, that would be, if these were all straight, everything was straight there, even though it's rounded here and there, that would be a cylinder. anything that goes, any shape that you have in a plane, extend infinitely upward and downward, that's a cylinder. Okay? Doesn't have to be a circular cylinder. So get used to that. Okay. Now, here's a picture of that cylinder. Okay? Notice in the xy plane, that would be x minus a squared plus y minus b squared. This is your a, that's your b. Y minus b squared is equal to r squared. That would be the circle if you're in 2 space. But if you're in 3 space and your problem tells you that, you extend that circle up and down infinitely along the parallel to the z-axis. Let z be any value for the right circular cylinder of radius r centered at AB0. So just looking at the formulas alone, the equations alone, you can't tell a difference between a circle in 2 space and a cylinder in 3 space. Right circular cylinder in 3 space. But if you're told where you are, that is what defines it. Okay. Now, what's that?
I think this is example 1.
This is example 1. Okay, good deal. Thanks. Okay. Describe the set of points, I shouldn't have brought this up yet, defined by the following conditions. These are not equations, these are conditions. X squared plus y squared plus z squared is equal to 4, comma, y is greater than or equal to 0. If it didn't have that second part on it, what would it be? X squared plus y squared plus z squared is equal to 4. That would be a
Circle. Sphere.
sphere, because it's 3 dimensions. Sphere of radius. Maybe I should write it down because not all of you have books. Yeah, of radius 2. This would be, okay, I've got, as soon as I go to right, it's going to shrink. Well, there you see it. There you see the radius 2. They indicate that's a 2, that's a 2, this is a 2. Okay. Minus 2 down here. Right there. Okay. But when they say y is greater than or equal to 0, that means a hemisphere. Half of a sphere. You cut off the y is equal to the negative y, half of the sphere. Okay? Now, this next one here, as soon as I write, it's going to shrink. And even before I write, it's going to shrink. Let's see if I've still got my pen. This would be x minus 3 squared plus y minus 2 squared plus z plus 1 squared. Okay? No, sorry about that. This is okay. Sorry about this. Hold on. Let me get my eraser. I was doing a sphere. It's not a sphere. Okay. So awkward. Here we go. Okay. What is the radius here? 1. 1 squared is 1. Okay. That would be, if that's all you had, but you said this is in 3 space, what would that be? A cylinder of rate at what center? 3, 2. 3, 2. And the point through 3, 2, parallel to the z-axis, would go infinitely top and bottom. But what changes here? You see light line here means it extends upward. This dark circle here means it stops right there at z is equal to -1. So this would be z greater than or equal to -1. So the second part of this would be z greater than or equal to -1. Okay, and that's exactly what they list here. X minus 3 squared plus y minus 2 squared is equal to 1, where z is greater than or equal to -1. That's the figure for that equation. In 3 space, okay, it wouldn't make any sense otherwise. All right, that is sort of your analytical geometry, or a little bit of that. Let's now move to the vector representation of the same, similar type stuff, okay? Now, all right. Nope. Trouble getting the right slide to come up. Okay. Now, we got used to vectors in 2 space. And guess what? In a sense, a vector is only a one-dimensional object. But that one-dimensional object, because all it has is a magnitude, a length. It doesn't have an area, it doesn't have a volume. So it is a one-dimensional object. But it can exist in 3 space or 2 space. We've seen them in 2 space. Now this is 3 space. What it means, the initial point and the final point, the initial point and the terminal point, could have and do have dimensions or values in varying x's and y's and z's. Okay? So here is a vector PQ, arrow starting at P going to Q, so the arrow would be that way, whose coordinate, now these are coordinates, not components, coordinates, 3, 3, 2 for P and 5, 7, 4 for Q. Now, this vector PQ is a one-dimensional shape, only has a length, but it's in 3 space. What would be its components? The vector, this one here, as soon as I go to right, of course, it's going to reduce. Well, I think I already have my. So the vector PQ has what components? This one right here.
1 and 0.
Okay, no, it has all 3 components. What is it? Remember from before? It's the x2 minus x1, comma, y2 minus y1. Now all we do is
2.
z, yeah, okay, so that would be 2, comma, 4, comma, 2. That's it. Vector PQ would have components 2, 4, 2. The difference in your x's are 2, and the y's are 4, and the z's are 2. Okay? Viewed this way, difference between 3 and 5 is 7, so that has a vector component in the x direction of 2 and the y direction of 4. So that would have been in the plane 2, 4, but then when you include the z, it's elevated up this way another 2. So 2, 2, 4, 2, that vector would be, you could draw it down here exactly parallel to that. Okay? 2, 4, 2. Now, again, drawing vectors in 2 dimensionals, and on a 2-dimensional thing representing 3 dimensions, really hard to tell which way that thing's pointing. I mean, you might think that's pointing in the XY plane. It could be pointing backwards in the XY plane. It's pointing this way, further out, positive in X, positive in Y, and positive in Z. So it's away from the origin of the number. Exactly. Okay. So there is your vector in 3 space. Now, I may not have given the same nomenclature as the book did. Let's find that. Oh, here it is. All right. Now, before we go any further, you tell me the length or the magnitude of that vector. And that PQ is also called vector V. So what's the magnitude? Now for vectors, they use a double bar. V, and since I can't write bold, I'll write it with an arrow on top. What would be the magnitude of that? Hint, hint. 2 squared plus 4 squared plus 2 squared, which would be the square root of 24. Or you could write that if you chose to. That's 4 times 6, right? 2 root 6. Okay. You don't have to do that, but you can. Should I say plus or minus? I forget. No, remember, I don't forget. No, it's always positive. Always positive. Always positive. Okay. Good deal. Okay, so there's its length. And generically, it would be this for any vector x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. Okay, for any vector like that, then it would be the square root of x2 minus x1 squared plus y2 minus y2 minus y1 squared plus 2 minus z1 squared. Okay. I didn't write all that out, but hopefully you got it. Okay. They call it a2 minus a1, whatever you want to call it. Fine. All right. The terminology and basic properties discussed in the previous section carry over into R3 with little change. So let me clear this slide. Okay, and write these down. A vector V, and why did it do that? Okay, well, wait. All right, vector V is said to undergo a translation. Okay, what does that mean? Vector V undergoes a translation.
It's got the same direction and magnitude still.
Yeah, its direction and magnitude cannot change, but its location can. Anywhere in 3 space. Back into the board here, but the magnitude and direction cannot change. That's what we mean by translation. So its magnitude will remain the same and its direction will. Vector V is said to undergo a translation if it is moved without changing direction or magnitude. Okay? What do we mean by 2 vectors V and W being equivalent? Same magnitude and direction. Think of it this way. Equally sounds like equal value, meaning everything about them is the same. Magnitude and direction is the same, so they are. So this, if that were V and this were W, or that were W, that were W, as long as the magnitude and direction have not changed, they are equivalent. Okay? If you've translated them, is another way. Okay. Two non-zero vectors V and W are parallel. What does that mean?
It means they're parallel. So it means they have the same direction.
Same direction. Their magnitudes can be way off, opposite, whatever, but the directions are the same or exactly opposite the same. Those are both considered parallel. Let's see how they say it. Two non-zero vectors V and W are parallel if V, here's the way they say it, if V is equal to lambda W for any possible scalar value lambda. Non-zero, okay? They didn't say this. Lambda not equal to 0. Technically, 0 is parallel to any other vector. But for it to make sense, don't even go there, okay? Because then you can't say they have the same direction because 0 vector has no direction. So I like to say a non-zero. The book doesn't specify that, but technically, I think you almost have to. Okay. Now, what do we mean by position vector? What would be the position vector for that?
Where it's placed at.
Say again?
Where it's placed at.
Wait, Lauren. I can't get this to come on. There we go. Yuck. Okay. I think I got it. Nope.
Where it's at based on the origin.
I can't get this to pick up a different... I did. Okay. The position vector would be based at the origin, but everything else the same. Magnitude the same, direction the same, everything the same, but based at the origin. That's called the position vector. Okay? The position vector of a point Q0 is the vector V0, which is the origin to Q0, based on the origin in figure 9. Okay, let's go to figure 9 then. Here is a new vector V, P, Q, like this. Its position vector, move P, translate P back to the origin, keeping everything else the same. That then puts your Q0 up here. Remember this vector V, now these are angle brackets here. It's hard to see from where you're sitting, I'm sure. Even if I blow it up, I think it'll be hard to see, especially if I blow it up with too much dynamite. Okay. These are angle brackets, A, B, C. If I move that to where its initial point is at the origin, then the vector V0 is the same, vector ABC, but now Q0 is the point, parentheses, ABC, okay? Because then its terminal point will have the same components that the coordinates that the vector has as components, okay? Its translate, or its translation, is based at origin. That's what the position vector is. Okay? In the XY plane, then its position is also, the initial point is at the origin, and whatever the Y, we refer to the angle between the x equals 0 axis to there. Here we can't define or haven't defined that yet, so don't worry about that yet. Okay. It's an apple stuck in my tooth and it's really bugging me. Okay. A vector V, PQ, with components A, B, C is equivalent to the vector. Yeah, we just said that. Okay. The components V of PQ, V equal PQ, where P is, of course, if we go to right here, it's going to shrink. Well, I think no, go back to black. Don't think it'll let me get to black, so I'll go to the next best thing. It's a very deep purple. Used to be a singing group, by the way. The components of V, PQ. So if this P, now that's a point, so it has parentheses, A1, B1, C1. And Q is a point. Let's call that A2, B2, C2. Okay? That means in place C2. Okay? The components of the vector V, which is PQ, P being the initial point, Q being the terminal point, so that vector right there, what would be its components? Second, we did something very similar to this before, so it shouldn't be new. It's what? A little louder? 8. A2 minus A1. Better probably put in parentheses. Comma. Ooh. B2 minus B1. Close parentheses. C2 minus C1. Close angle bracket. That's the vector. Okay? Okay. Okay. And each one of these are the components. Components in the X direction, components in the Y direction, and components in the Z direction. Remember, the order still matters. Ordered triplet now, not ordered pairs, ordered triplet. Okay. Now, another rather strange way they express this, it's perfectly fine, but that would be OQ minus OP. Because OP plus V would be OQ, so OQ would be I did say it right, didn't I? OQ minus OP, yeah. So OQ minus OP. Okay. We usually don't go around doing that, but you could. Okay. So here's an example. What if P were 3, negative 4, negative 4? Obviously not this one, but P equal 3, negative 4, negative 4. Q is, I had it somewhere, there it is, 2, 5, negative 1. Remember, these are points. 2, 5, negative 1. What would be the vector V that is PQ? Going to be a vector, it'd be a negative 1. 9, very good. 3, excellent. Okay, there it is, negative 1, 9, 3. Very good. Two vectors are equivalent, and we've already sort of said this one, if and only if they have the same components. Okay? If they are same magnitude and same direction, no matter where you have those two, if they are, then that means the components would be identically the same. Okay? I think we already said that. Vector addition and scalar multiplication are exactly like defined for the two-dimensional sense case. Vector addition is defined by the parallelogram law. That's now in 3 dimensions, not 2. And they do show figure 10 here. So if you're adding, let me blow this up. All right. If you're adding vector V plus vector W, then take the vector W, put the tail of W on the tip of V, and then from the tail of V to the tip of W would then be V plus W. Okay? Now, say something else, but that might be just confusing. All right. Do we want to do the parallelogram law? I sure don't, because that means drawing 3-dimensional vectors in 2 space, which is already a pain in the neck, and then having to add them in that same 2 space is a bigger pain in the neck. How's a better way to do this? Say again? What's that? Yeah, adding components. That's always so easy. Get them into component form and add the components. Okay. And that's what they say next. In terms of components, if V, now of course when I go to write this, okay. If V, vector V, is V1, V2, V3, we're going to stay in 3 space, I don't think we'll go beyond that, and vector W, vector is, angle bracket, W1, W2, W3, okay? Now, why they do scalar multiplication first, I just as soon do vector addition first. What would V1, V plus W be? Number 1 is also going to be a vector. Okay, and what would it be? V1 plus W1, comma, V2 plus W2, comma, V3 plus W3. Can you get any easier than that? What would we mean by lambda V? That is going to be a vector too, and it'll just be lambda V1, comma, lambda V2, comma, lambda V3. Okay? I'll sneak one in on you. What would be the magnitude of lambda V? It's not in the book. Well, that's going to be the square root of lambda V1 squared plus lambda V2 squared plus lambda V3 squared, which would be square root of lambda squared V1 squared plus lambda squared V2 squared plus lambda squared V3 squared. Factor out a lambda squared and then take a square root of that. You just have lambda times square root of V1 squared plus V2 squared plus V3 squared, which would be lambda V. So hopefully you were expecting that, but if not, that's what it is. They didn't give it here. But vector addition is commutative, associative, and it satisfies distributive properties with respect to scalar multiplication only. Okay, don't try multiplying vectors using distributive law. don't do it. So let's do example 2. I think I've already done some things around that, and I don't think they give us any graphic for this, or maybe they do. Is figure 11 the graphic for this one, or is that for example 3? Huh? That is example 2, so I guess we can use it. The trouble is, they already give you the answer. Oh, wait. Here's the 2 I just wrote down. I have a hard time remembering which have slides and which don't. Okay. Lambda V is lambda times vector V, which is A1, B1, C1. I would call it V1. V. Okay. V1, V2, V3. So that would be lambda times each of the lambda A1, lambda A2. Lambda A1, lambda B1, lambda C1. And vector addition would just be A1 plus A2, comma, B1 plus B2, comma, C1 plus C2. I was calling this B1, B2, and B3, this W1, W2, W3. Same thing. Whatever you name them, whatever subscripts you give them, you add the corresponding components together and you get it. Okay. All right, so let's do, all right. Here they've done too much for us. And I'll blow it up to begin with, but then when I go to write, it's going to shrink back. Okay. Calculate the magnitude of V and 6 minus 1/2 W, where V is, of course here I'll go to shrink, all right. Well, yuck. Why did that happen? Okay, now we got it. V, vector V, is the vector, angle bracket, 3, -1, 2. And you see, in the book, you really have to be careful that you're writing angle bracket rather than parentheses. They really have them very shallow. And here's W, vector W. I like to make them obvious, okay? 4, 6, -8. Okay. With that in mind, the first thing they said is calculate. What a pain in the neck this is. Magnitude of V. What would that be? I already gave you really most of it, putting the square root sign there. What do I put inside there? A little louder? 3 squared plus, second? Okay, how about the -1 squared? Don't forget that one. Okay, plus 2 squared. Okay. It doesn't matter what order you do them, but most of the time we keep them in the order. What does this give you? Oh, sorry. Oh, this is example 2. Have you got a different example 2? Are you in the old book or new book? Okay, that might be a problem. What is your example 2?
It's the same thing, but the example 3, I thought example 3 when we figured it out.
Oh, okay. All right. So what do I go from here? This is a little louder. Okay, yeah, 9 plus 1 is 10, plus 4 is 14, square root of 14. Perfect. Okay, that's all you need for that. Okay, now the next one says, what is 6V minus 1/2 W? Number one, it's going to be a vector. Okay? What you reckon that vector is going to be? A little louder? Okay. It would be, I'm sorry. Okay. All right. Okay. 6 times vector v. And what would that be? I'll write it out. 3, negative 1, 2, minus 1/2 of vector w, 4, 6, minus 8. Yuck. This is so awkward. Okay.
Is that 0, 8?
It was a mess. Negative 8. Okay. Well, what's 6 times that? Okay. So, yeah, this would be 18, negative 6, 12, minus, 1/2 of that, 2, 3, negative 4. And when you add those together, you get, second, no, this is a minus in between. Wait, no, you're right. That's an 18. I can't read my writing. You're right. 16, negative 9, 16. Very good. Okay. And let's see. How did they? They got it right. Good for them. Now, new subject. If vectors v and w are parallel, then there must be some scalar lambda such that v is equal to lambda w. Thus, let me clear this for now. Oh yeah, that's not the one I wanted to go to. All right. Here's a vector, 3, negative 1, 2. Lambda times some vector that's parallel to that, 4, 6, negative 8. Okay. Now, can that be true? This is saying that 3 is equal to 4 lambda, but also negative 1 is equal to 6 lambda, but also 2 is equal to negative 8 lambda. Okay? I think this is the easy one. This is a lambda is equal to negative 1/6, wouldn't it? Okay? Then if you did this, 3, is that equal to 4 times a negative 1/6? Ain't no way. Okay? Not going to work. Okay? It can't satisfy the others, so therefore those two vectors are not parallel. So that's how you test for parallelism. Just set the components to equal, one vector is a multiple, generally a non-zero multiple of the other one, and see if you can get them to work. That one, you could look at it and tell it wasn't going to work, basically. They're not parallel. Usually a pretty easy thing to say. Now, where this figure is coming in is dealing with the second part. Actually, nothing to do with that exercise. These are our standard basis vectors in R2. Okay? Along the x-axis, we want 1 unit here, and boy, their scales here just drive me nuts, okay? That's supposed to be 1 unit here, that's supposed to be 1 unit in the y direction, that's supposed to be 1 unit in the z direction. Why this one is foreshortened so badly, you know, I can sort of see a little bit, but that just seems like it's way too much. Those are all unit vectors, okay? So whereas they write them just as bold, when I write a unit vector, I put a little hat over it, just to remind myself that those are indeed unit vectors. Now, here's that same vector v, I think that we had before, maybe not. No, because that had a negative component. These are all positive. Here's a vector v, ai plus bj plus ck. And basically, well, the vector v is abc, okay? And how you write that as a sum of components. So this would be, this is component form, this is the sum of component forms. Sum of your component unit vector form, you know, if you want to really get technical with it, okay? This would be AIs, see, this looks like A could be 1, 2, maybe 3. A would be 3I plus, that's your J, 1, 2, 3, looks like 4J plus, if this is 1 and K, 2, 3, maybe 3K, okay? But whatever it is, even if they weren't whole numbers like that, they would be AI plus BJ plus CK. By definition, if that vector ABC is unit vectors IJ and K, that's what it's got to be. Okay? Now, again, how do you add those vectors? You can do tip to tail as we did before, but you know, without the actual numbers here, it's going to be a little harder. And this would be, I think we're saying 3I plus 4J would be that then, plus, okay, 3K, that would be up there. Okay. Let's do example 3. No, this has not got anything to do with that one at all. So let's go back to this and remove all the writing. Okay, this is not that figure, but we're going to use it. Find the vector, unit vector EV. Word, this is driving me nuts. Okay, what I have to do is get rid of that. Okay. My pen back again. Okay. E V, where I think E is always considered to be a unit vector in the direction of vector V, where it says it's in the direction of V, where V is 3I plus 2J minus 4K. So that's why I know this picture doesn't go along with it, because there everything is positive. A, B, and C are positive. Not here. Okay? So, what you want is a vector that's a unit vector in that direction. How in the world are we going to do that? Find what? Now let the direction be just in the variables. Okay? Give it to you. Okay, we certainly want to find the length. I'm not sure you know why yet, but we do need to do that. So the magnitude of V is what?
Three squared plus
3 squared plus 2 squared plus a negative 4 squared, which is the square root of, say again?
square root of 29.
Okay, 9 plus 4 is 13 plus 12. No, I mean plus 16 is 29. Okay, good prime number, so can't do anything with that. What do we do with that, though? You found it, but what you going to do with it? Do you remember what? Okay. Here's a simple formula. Okay. That's what your unit vector in the direction of v, see this has to be in the direction of v because you're just multiplying it by a scalar, right? But that scalar we choose to be 1 over the magnitude, so that basically we're what they call normalizing that vector, making it a vector in the same direction but with a magnitude of 1. And that's exactly what we're doing here. And this would then be, and there's several ways you could write it. I like component, well, since they wrote the original vector in sum of unit components for, form, let's do the same thing. So what would this be? 3 over root 29I plus 2 over root 29J, yuck, minus 4 over root 29K. Got it. I don't know if that's how, yes, look at that. That's how they wrote it. 3 over root 29, except they wrote it in component notation. I mean, in vector notation with components in angle brackets. Since they gave you the problem initially in the other way, I thought they'd do this, but fine, it's a perfectly good form.
That makes too much sense.
What's that?
That would make too much sense.
Yeah, I'm afraid so. Okay. All right. What's that? Yeah, you got to get to the other class real fast. Okay, sorry about that. All right, we will start next time on parametric equations of a line. And homework exercises for this section. Where is my paper? Is that it? Right there. Will be either 1 or 3 or both, either 5 or 7 or both. Goodness, I can't see, that blinds me. Either 9 or 11 or both. Do 13. Do either 15 or 17 or both. And I think we can do more. 15 or 17 or both. 19, any of the odds 19 to 23. Any of the odds either 25 or 27 or both. Either 29 or 31 or both. And stop there. Stop at 31. And we'll pick up from there for next time. We'll see you Wednesday. Good deal. Now I'll turn off the projector. And in the show, discarding the other stuff, and that,